So let's introduce accumulated local effects, also known as plots, which are a great visualization tool for feature effect. We will start this chapter by introducing the extrapolation issue the partial dependence plots suffer from, which is a property that is sometimes unwanted. We will look at plots that can get rid of this extrapolation issue, however, introduce omitted variable bias, which is, I would say, a much bigger issue. In the end, we will introduce details of plot and its estimation procedure and understand them better. To better understand the extrapolation issue, let's look at a simple example. We have here on the left-hand side two features, x1 and x2, which are correlated. The black points are our data points that are observed and part of our data. The red points are the artificial grid points that the partial dependence plot creates and asks the model for their predictions, which are then used in the partial dependence plot to visualize it. On the right-hand side, we show an example where we use the marginal distribution of the feature x2. Basically, the partial dependence plot at each position of a grid point, for example, at the position of 0 for x1, it averages the predictions using the marginal distribution of x2. This means that it takes into account all feature values of x2. In the end, the partial dependence plot averages over predictions that are in these regions where we usually don't have any observed data points. This can be misleading when we interpret the partial dependence plot, especially if the model itself contains interactions. This can be a not wanted behavior, as we will see in an example in a few seconds. One thing to note here is that partial dependence plots don't do anything wrong here. They basically describe the feature effect that the model estimated itself. Thereby, it takes into account also points that are outside the observed data distribution, because the model will also give you prediction for these regions, although the points are unrealistic. Using them will then lead to a bias in the interpretation. If one is interested in interpreting the feature effect within the data distribution, then this might be an unwanted behavior. Let's make a simple example to illustrate this fact. So we sample from a uniform distribution 5,000 data points. Also, we will sample a random small noise and generate two features, x1 and x2, which are strongly correlated, as we can see here in the graph. The two features are positively correlated because they follow a straight line. So the data generating process is then defined here as the sum of feature x1 and feature x2 to the square, with again a small noise. This is how we generated our data. We have two features, x1 and x2, and our target y. Using this data, we fit two models. On the one hand side, we fit a neural network and a correct specified polynomial model, which means that we exactly use the quadratic feature x2 and the linear feature x1 in the model and fit our polynomial regression model here. Of course, directly using this information will give us a very good performance of our model, which we estimated using cross-validation. So the neural network on the left-hand side will also give us a good performance. On the right-hand side, since we specified a polynomial, this will look like a quadratic polynomial in this two-dimensional space here. On the left-hand side, we fitted a neural network. Although the performance of the model is pretty similar to the correct specified polynomial, we see that the prediction surface here looks completely different than on the right-hand side. This means that neural networks in regions where we don't have data points will still give you predictions, but behave somehow a bit strange in these regions. At the same time, since the performance of the neural network here is pretty close to the one of the polynomial model within the data distribution, the prediction surface will look very similar. This is a known behavior of neural networks since they are so flexible and can be very complex models. So if we want to visualize the feature effects of the fitted model, we would expect a linear effect for feature x1 and a quadratic effect for feature x2. Now, before we introduce AL plots, we will just look at the result and compare it to the result of partial dependence plot. So here we see AL plots of both features in the first line here and compare it with the true marginal effect. Like I said, the red line will reflect the marginal effect of x1, which is a linear effect, and on the right-hand side, the quadratic effect that is also visualized here in red. As you can see, the AL plot that is computed afterwards will be very close to these marginal effects that we would expect. Below, we see what the partial dependence would do. Apparently, the red line, which is the true marginal effect, doesn't really match the black line, which is the partial dependence plot that is estimated. Still, the partial dependence plot shows what the model does in its expectation. However, since we have a lot of interactions in our neural network, and since partial dependence plot average points outside the data distribution, we get these biased results that do not really match with the original true marginal effect. Although the model itself has a similar performance as the correctly specified polynomial model. Basically, one can say that partial dependence plots give you interpretation that are true to the model because they describe the effect that the model estimated. And AL plots are more true to the data because they reflect also the effect that we would expect by looking at the data generating process. So one might argue that one can get rid of this issue by just avoiding evaluating data points outside the data distribution. And we will see in an example that M-plots are doing this, but introduce another issue. Again, what partial dependence plot does is that it averages predictions over the marginal distribution. Okay, if this is an issue that evaluating data points here will lead to a bias in our partial dependence plots, why not simply average using the conditional distribution, which ensures that we are only looking at points that are close to the conditional distribution of x2 given a certain value for x1. This is what M-plots are doing. Instead of just using the whole range of values for x2 and averaging for all of these values, we are defining a neighborhood set of observations that are close and only average exactly these points that are in the neighborhood. This way, we can approximate the conditional distribution, which is more local to the value of x1. So to sum up, M-plots average the prediction over the conditional distribution, which is useful in the sense that we avoid the extrapolation issue because we don't take into account data points that are outside this distribution as partial dependence plots do. However, this will introduce an issue called the omitted variable bias. Essentially, doing this will lead to marginal effects that also contain effects of other features that are dependent. We will make an example in the next slide to understand this better. This would make M-plots completely useless in assessing the feature's marginal effect, especially if feature dependencies are present, which is often the case in real life. So let's look at the omitted variable bias problem. For this, we have simulated two features that are correlated, x1 and x2. Here you see the correlation of both features. And we have visualized the true function of the marginal effect that we have described in here. Basically, the true function of the marginal effect of x1 is a linear line with negative slope. So estimating the marginal effect of our loss optimal model here, we would expect a linear line with slope -1. Since we don't have any interactions here, the partial dependence plot won't suffer from an extrapolation issue and will do a good job, which is a blue line here that we can see that matches the red line pretty well. Now, looking at the M-plot that is based on using the conditional distribution will result in an issue. We see a completely different curve here And the reason is that basically it takes into account the effect of the second feature. So basically the effect of the second feature and the first feature are summed up. So -1, which is the effect or the slope of the first feature, is summed up with +2, leading to a marginal effect that has a positive slope, which is then shown here in the marginal plot. So the M plot essentially mixes the marginal effect of feature x1 and x2 and visualizes it, which is an unwanted behavior if you are only interested in the marginal effect of x1. To get rid of this issue, L plots are based on the idea of integrating partial derivatives. Basically, to remove unwanted effects of other features, like we have seen in the M plot, we can first take the partial derivative of the prediction function with respect to the feature of interest and integrate it with respect to the same feature. Using the partial derivative of the prediction function removes other main effects, and integrating it again will recover the main effect of the feature of interest, xj. Let's look at an example. Here we have two features and one interaction. Now using the partial derivative with respect to x1 will give us this term here. What happened here is that this term is vanishing due to the partial derivative. And this is exactly the term that would include the effect of feature x2. So this removes the main effect of feature x2. Integrating this partial derivative again will recover the original function without the main effect from before. As you can see, the interaction with features that belong to feature x1 and any other feature will be still present here, which could cause some issues, but at least we removed the main effect. If we would have interactions of other features, for example, x2 and x3, they would have been also dropped using the partial derivative. We know that M plots suffer from the omitted variable bias, which means that it includes main effects of other features that are dependent with the feature of interest. We achieved the goal here by using this idea of integrating the partial derivative. And L plots are using this idea. They do not suffer from the extrapolation issue because they are based on a similar idea as M plots, and they also don't suffer from the omitted variable issue because it is based on integrating partial derivatives. And as we have seen, we get rid of the main effects of other features using this idea. The estimation of L plots is based on 3 steps. First of all, we estimate the local effect using the partial derivative. To be more specific, the partial derivative is estimated using finite differences. We will see this later on. And evaluated at certain points. After having computed the local effects, we will average these local effects over the conditional distribution, similar to what M plots do, to avoid the extrapolation issue. To recover the original main effect, we integrate in a third step the local effect up to a specific value that we want to visualize. This allows us to estimate a global main effect for the feature of interest and avoids the omitted variable issue, as the other unwanted main effects were removed due to the partial derivative in the first step. All these 3 steps that we have mentioned can be put together into one single formula, which is the so-called uncentered first order ALE function. We have referenced all these 3 steps here in this formula. First, the partial derivatives, the expectation of the partial derivatives, which are the local effects basically at a certain point evaluated at x s equals zs, and the last step, the accumulation, so the integration up to a certain value x. So don't be scared about this probably complicated formula. We will have an example later on. Important to note is that this is the ALE function for feature of interest S. Again, the first step, we are taking the partial derivatives of the prediction function with respect to the feature of interest. Remember that this will remove all main effect of other features to avoid the omitted variable bias as in mplot. Then we are using the expectation evaluated at this point ZS to average the local effects. So essentially, here we have an aggregate of local effects. After averaging these local effects, we are integrating them up to a certain point X in order to be able to visualize it. But again, we will see this in an example later on. What is usually done is to center the uncentered ale. This can be achieved by subtracting the average of the uncentered ales. This results in effect plots that are centered around 0. This is similar to the effect plots that generalized additive models give us, and different to what a partial dependence plot produces, because the partial dependence plot is not centered around 0. Although, of course, you could also center the partial dependence plot so that it has 0 mean. So this is the constant value with which we subtract the uncentered first order AL plot. So now we have talked about the theoretical part of AL plots. Now we will look into how to estimate AL plots. First issue is that partial derivatives are not useful for all models. For example, for trees-based methods such as decision trees or random forests. However, we can use an approximation by finite differences. Basically, the idea is to segment the range of values of the feature of interest into k intervals and to call the interval bounds z. If we start with the index 0, we will have in total k plus 1 z values here that are used to define intervals, where z0 is the minimum value of the feature of interest and zk is the maximum value. A simple way to create intervals is to use as interval bounds quantile values. Let's look at the illustration. On the left-hand side is again our example where we have two correlated features, x1 and x2, for which we want to compute an AL plot. We start with focusing on feature x1 as the feature of interest. This means that we can segment the values of x1 into k intervals. Here we have chosen k equals 4 because we have 4 intervals here. For each point within an interval, we are replacing the feature value of x1 with the interval bounds. For example, here and here we will have 2 points that refer to this one data point that we have here. We are asking the model the prediction at these points and compute the prediction difference with the upper and lower interval bound. This will essentially be the finite difference to compute the local effect of an individual observation here. So for each interval, we will average these finite differences and then accumulate it up to a certain point. If we have here observation I with this value for the feature of interest, we segment this into its corresponding interval. We are only replacing the feature value for feature of interest. In this example, we talked about feature x1. All other feature values are kept constant. The finite differences basically then correspond to using the prediction model f hat and replacing the original feature value xsi with the interval bounds here and here. And then we compute the prediction difference. We do this for all points within an interval and estimate or approximate the local effect within each interval by averaging all finite differences. This is an approximation of the expectation with respect to the conditional distribution of the previous formula we have seen. As the AL function, we have f of x for feature s, for example, and let's say the x value will be here, for example. We basically sum up all local effects up to this point of interest. So in this example, for this interval and this interval, and probably also for this interval. Here we can try to write down the estimate of AL plot into a formula. First of all, let's introduce what we have defined here. We have Ks, which denotes the interval index of a feature value from the feature of interest. This tells us in which interval we are currently looking at. And then we have as notation ns the number of observations inside this interval. This here is then basically the average of all local finite differences within a certain interval. And we are summing this up to the interval where the value x lie, as I have previously described this guy here, including this interval. In order to have a mean-centered AL plot, we subtract the mean value. Here a summary of the algorithm. We first create k intervals across the whole feature space of the considered feature of interest. And for each interval, we repeat the following two steps. We replace the feature value with the upper and lower interval bound for all observations inside the kth interval. For each observation, we then compute the finite difference inside its corresponding interval. And for each interval, we average all these finite differences to obtain per interval an approximate local effect. In order to obtain a curve that we can visualize, we accumulate the interval-wise local effect up to the value of interest, and then use the aforementioned formulas to compute the uncentered AL and center it to have zero mean. Here we applied the AL plot on our bike sharing dataset. The first line, just as a comparison, computes the partial dependence plot of the feature humidity and the feature temperature. Below, we have the first order ALs of both features. We can easily see that the shape of both the partial dependence and AL plot are very similar. And because we are mean centering the AL plots, we see that the y-axis here is different than the one from the partial dependence plot because it's mean centered. Second order AL plot exists as well. On the left hand side, we see the bivariate partial dependence plot. On the right hand side, the second order AL. There's a difference here. While for the two-dimensional partial dependence plot, the main effects also are included, this is not true for the second order AL plot. This is a nice property of AL plots because we directly understand where interactions are present and where not. For example, if there wouldn't be an interaction between temperature and humidity, the surface would be completely at zero. And it looks like this in most parts of the feature space. But here there are some region where there might be an interaction. Essentially, this means that for high values of temperature and high values of humidity, there might be an interaction. Also for low values for temperature and high humidity, there might be also a little interaction. Now let's compare some properties of partial dependence plot and AL plot. Just remember that partial dependence directly averages the predictions over the marginal distribution, which can lead to the extrapolation issue. The first difference of AL plot is that AL averages the change of predictions, which are computed by partial derivatives. And in the estimation process, we have used the finite differences here. These change of predictions are averaged using the conditional distribution. Similar to the M-plot, this ensures that we avoid to extrapolate in regions where we don't have many data points. The second difference is that ALE integrates partial derivatives of a feature. This integration of partial derivatives isolates the effect of the feature S, meaning that it removes all other main effects that are dependent on this feature. The third difference is that ALE is always centered. It has zero mean. Basically, it is vertically centered so that the function, the curve, is moving around the zero line. To make ALE plots and partial dependence plot visually comparable, we can do a similar procedure for partial dependence plots and center them as well. Another advantage of ALE plots compared to partial dependence plots are their computation time. Since for each observation we only have to compute 2 predictions for the lower and upper bound of each interval, it is much faster than, for example, partial dependence plot, where for each observation we usually compute multiple ice curves, which are then aggregated